The longest common subsequence problem can be better explained with an example. And as an example, we would like to use the DNA similarity problem. So we know that a strand of DNA consists of a string of molecules called bases. So if we have a string of DNA, it consists of molecules known as bases. And these bases are adenine, represented using the letter A, guanine, represented using the letter G, cytosine using C, and thymine using T. So as I said, DNA can be expressed as a string of these characters A, B, A, C, G, and T. Now, in the DNA similarity finding problem, what we would like to do is compare a DNA to two or more different DNAs. Typically, we have organism 1, which has a strand S1 that looks something like this. And then we have organism 2 with a strand S2 that looks something like this. And now, to see how similar these two organisms are, what we would like to do is measure the similarity between these two strands. So basically what we want to do is find a third strand, S3, such that in this strand S3, let's say that has these characters in it, these characters should appear both in S1 and S2, but then they should be such that they appear in the same order. That is, whatever order these sequences are here, they should appear in S1 and S2 in the same order, but not necessarily consecutively. So if I have CCG in my strand S3, then let's check if CCG appears in that order or not. So CCG appears in that order, but they also appear consecutively. In the second sequence S2, we have CCG. So they are still in the order, but they are not necessarily consecutive to each other. So in this way, we can calculate similarity between these two strands S1 and S2 by trying to find a third strand S3 that has bases common to both of them. So we want to continue to increase S3 and find how long that is. Let us also define what a subsequence is. So given a sequence X that looks like this, say for example with characters A, B, C, B, D, A, B, then we say that Z is a subsequence of X such that all the characters in G appear in X in the same order. So in this case, we see that B, D, and C map to C and B map to X, and they're in the same order, and the order is 2, 3, 5, 7. So all the characters in G map to the sequence X, and they are in the order. So in such a scenario, we can say that Z is a subsequence of X. Formally, given a sequence X that has characters X1 through Xm, we say that Z1 through Zk is a subsequence of X. Obviously, K should not be more than M. Subsequence of X if there exists an increasing sequence I1 through Ik in our sequence X, such that all the J1 through K, for all the J1 through K, we have a mapping between Xi and Zj. Next, let us see what a common subsequence is and also what a longest common subsequence is. We say that Z is a common subsequence of two sequences X and Y if Z is a subsequence of X and it is a subsequence of Y as well. Here's an example. Say we have our sequence X that looks like this, and then we have another sequence Y that looks like this. Then we say that a sequence BCA is a common subsequence of X and Y because we have BCA as a subsequence of X, and we also have BCA as a subsequence of Y. Now, if you observe carefully, you will see that BCA is not the longest common subsequence, however, it is one of the subsequences, but not the longest one. So if we look at these two sequences and try to find the longest common subsequence, then we will see that there are actually three longest common subsequences. So there are actually not two, but three longest common subsequences. One is BCAB. So BCAB is here. BCAB is here. The next is BCBA, BCBA, and BCBA. And the other is BDAB. That would be BDAB and BDAB. So in this case, we have actually four longest common subsequences. So formally, we say that the LCS problem is that given two sequences X and Y, where X is a sequence of characters X1 through Xm, and Y is a sequence of characters Y1 through Ym, the problem is to find the maximum length common subsequence of X and Y. So how do we solve the LCS problem? One naive approach to solve LCS problem is to use the brute force approach. Now, before we discuss the brute force approach, let's quickly see how many possible subsequences can we have for a sequence of length 3. Say I have a sequence of length 3, A, B, C, then the possible subsequences for the sequence are A, B, C. Those are three possible subsequences. A, B, A, C, and BC are three other possible subsequences. And then ABC itself is another subsequence. So we have 7 subsequences here. If I have X as a sequence of 4 characters, then the possible subsequences I can have are A, B, D single characters, A, B, A, C, A, D, and so on. You will see that we have 15 subsequences for A, B, C, D. So in general, we actually have 2 to the power here 3 minus 1, and here 2 to the power 4 minus 1. In other words, for a sequence of length n, we have approximately 2 to the power n possible subsequences. So now the idea behind the brute force approach is to take, say, 2 sequences S1, S2, 2 strands, and then enumerate all possible subsequences of X and also all possible subsequences of Y. So what we do is we do X equals, we list out all the possible subsequences, and then we also do Y equals, we list out all the possible subsequences. Now this obviously takes a lot of time in the order of 2 to the power m because X has that many subsequences, and same for Y. Now with that as input, in the second step, what we do is for each subsequence in X, we try to compare it with every possible subsequence in Y. So then we take the next subsequence of X, compare that with every possible subsequence in Y, and so on. We do pairwise comparison. And then we find the longest matching subsequence between the two. Obviously, this is going to require exponential time, and the algorithm is going to be very slow. So we need something that's more intelligent than basic brute force approach.